captain of the Sea and Space Rocket Club, and I have my L1 certification. I'm a junior studying aerospace engineering, and I will also be the safety officer during competition.
Hi, my name is Ritur Rangarajan. I'm the co-captain for CU in Space. I'm currently studying aerospace engineering, and I'm a sophomore. I'm also level 1 certified with Triple E.
Hi, my name is Alex Verga. I'm a junior in the aerospace engineering program at the University of Colorado Boulder. I am the project lead, and I am level 3 certified through Triple E.
My name's Bernadette Weigang. I'm a junior aerospace engineering student, and this is my first time doing rocketry.
Hello, my name is Akshay. I'm a second year mechanical engineer, and I am new to rocketry.
Hi, my name is Rachel Carlson. I'm a freshman studying aerospace engineering. I'm new to rocketry, but I'm currently working on my L1.
Hi, I'm Robin Sony. I'm a first year aerospace major with a minor in electrical engineering. I've been doing rocketry for a few years, but I never ended up getting any of my high power certifications.
Hello, this is our Argonia Cup video presentation by CU in Space. So to go over our rocket layout, we're going to be targeting for an apogee of 34,538 feet. This was taken off our open rocket sims. We're going to be hitting a max velocity of 2,035 feet per second, which is around Mach 1.8. And we're going to have stage separation of approximately 3,500 feet. So to go over the specific layout, so at the top here, we're going to have our golf ball packing structure. After that will be our sustainer parachutes, as well as our sustainer avionics, and then obviously the motor. Then in our booster section, we're going to have our parachute and the booster avionics. So here is our CP location, which is 35.87 inches from the aft end, and our CG location, which is 38.66 inches from the aft end, giving us a stability of 3.5. So for our rocket layout, here's our full assembly. It's going to have a dry mass of 2.131 kilograms and a wet mass of 6.29 kilograms. A total length of 90.55 inches. In our booster section, it's going to have a dry mass of 0.846 kilograms and a wet mass of 2.905 kilograms with a length of 37.36 inches. And our sustainer right here is going to have a mass of 1.286 kilograms and a wet mass of 3.386 kilograms with a length of 53.15 inches. So for our rocket materials, the things that we bought commercially were our rocket airframe, which is fiberglass, as well as our nose cone, also fiberglass. The nose cone was a 6:1 Von Karman with an aluminum tip. The things that we custom made were our avionics sleds, our fiberglass bulk plates that we're going to be using in the rocket, as well as our carbon fiber fins and our tip-to-tip layout. So one of the things that we as a club wanted to better our abilities in was to make our own composite components. So here are two examples of what we made that are going on that we'll be using for the Argonia competition. So we have a carbon fiber fin and our fiberglass bulk plate right here. The specific reason that we wanted to go into making our own composites is we're able to control the geometries. This was really highlighted in our fin because we were able to get a very specific airfoil geometry that allowed us to maximize our altitude and optimize the score as much as we could. And then here's a picture of our tip-to-tip layup that we did over that. This rocket is a minimum diameter, so there is no internal motor mount, it's only external fillets. So to make sure that we don't risk any fins falling off, to add extra security, obviously we wanted to do a tip-to-tip layup over the fins. So to go over our golf ball packing structure, here's a 2D sketch of what it would look like on the inside. So the structure itself is going to be the golf balls. We're going to have 6 of them total. It's going to be sectioned between the nose cone and the top of the sustainer airframe. So we're going to have a nose cone component as shown here, and our airframe component, which will house the respective number of golf balls. In between, we'll have a coupler, which is what mainly will be used to connect the whole system together. Just to show you how we pack. So here's our nose cone, and what we're going to do is our first bulk ball goes in. It's kind of hard to tell, but it's sitting along the sides of the nose cone, so it's friction fitted. And then we're gonna have our nose cone section goes on top. Press that in, obviously we'll put some golf balls in there. And then we have our coupler, which will just sit on top, and then it will compress this nose cone section down, so that way we prevent the golf balls from rattling at all. And then this here is our airframe section. So we're gonna have golf balls that go in here. This will sit on top as such, and then we're gonna have our bulk plate, which will sit on top here, so that the whole system will be compressed in this way, and then the whole thing slides into the sustainer. To go over our motors, so our net impulse is going to be 4,450 Newton seconds, which is well below the 5,120 Newton seconds as required by the competition. So for our booster motor, we're going to be using a Aerotech K480, which is White Lightning, an RMS 54 millimeter. It's going to have a total impulse of 2,295 Newton seconds. Here is the thrust curve for this motor. As you can see, it has a burn time of around 4.8 seconds. We chose this motor because we wanted to get our acceleration off the pad as high as possible, so that we can get to a good altitude before we ignight the sustainer. So allow it to coast for as long as we could. So here's our sustainer motor. We're going to be using an Aerotech K270 White Lightning. It's also an RMS 54 millimeter. Total impulse of 2,155 Newton seconds. This one has a much longer burn time, close to 8.7 seconds. The reason we chose this motor is because we wanted it to coast. We wanted a long burn time so that we could have much longer coast times to allow it to get to the highest possible altitude. All right, so to go over our recovery systems, so we'll be having a 50-inch thin wheel parachute in both stages. The Nomex parachute protector wrapped around it to protect it from ejection charges. To attach the parachute to the rocket itself, we're going to be using 3/8-inch Kevlar shock cord. These will be 12 feet in both stages. We'll be using quick links to secure all the various components together, so parachute, shock cord to the rocket itself. To get it attached to the rocket, we're going to have eye bolts, which will be mounted onto our bolt plates, and these eye bolts will be our mounting anchor points for parachutes. We also want to talk about the pyrotechnic line cutter. The reason we want to use a line cutter is because the rocket obviously has a small diameter. We are flying a minimum diameter rocket, so having a drogue and a main parachute would take a lot of room, a lot of weight. So to work around this, what we wanted to do is wrap when parachute. Obviously, when our ejection event happens, a parachute will come out, but it will stay wrapped up in a thick plastic band, which will run through the line cutter, and it will act as a streamer on descent. And at around 200 meters for both stages below, above ground level, we're gonna have our altimeters fire the line cutter, obviously cutting line, opening our parachute, and then bringing us down at a safe descent speed of 6 meters per second.
Thanks, Ratul. So now we'll talk briefly about some safety procedures. We have a ground test scheduled to ensure that we have proper charge sizing for both the booster and sustainer recovery events, in addition to the stage separation event. On launch day, our safety officer will be supervising the field prep of a rocket and going down our checklist to ensure that everything gets done. Only the 3 members with the most familiarity with the current rocket design and rocketry in general will be participating in prep to ensure the safety and success of our flight. So the aft end of our sustainer airframe is loosely fitted into the interstage coupler on top of the booster and should drag separate at burnout of the booster motor. As a backup, the egg timer proton located in the booster avionics bay will initiate a small black powder charge at booster burnout just to ensure that we separate directly at booster burnout. Now to talk about the sustainer inhibit logic. We chose a featherweight Blue Raven to handle the primary recovery events of the sustainer in addition to ignition of the sustainer motor. The Inhibit logic is programmed in accordance with the Argonia cup rules. So if the angle of attack is greater than 20 degrees and or if the velocity is less than 200 feet per second at the time of sustainer ignition, the sustainer motor will not ignite. Additionally, we are going to inhibit ignition of the sustainer motor if the angle of attack exceeds 35 degrees at any point during the boost or coast phase.
Thanks, Alex. Now let's talk about avionics. So in terms of our layout, we have two avionics bays, one for the sustainer and one for the booster. And they're marked here with the stars. And then our avionics base is comprised of two bulk plates, and then in between will be a coupler, and it's held together by two threaded rods. And on those threaded rods, we will have avionics studs. And right here is an example of an avionics stud that we will use. This is specifically for our sustainer. We will have a similar one for our booster. So, in terms of booster avionics, we have an egg timer proton altimeter, which is our primary, and then we have an egg timer quantum altimeter, which is our secondary or redundant. And then for tracking, we have a featherweight GPS. In terms of how the electronics are going to be connected, we have separate batteries for each altimeter, and then for each altimeter, we also have separate screw switches. This is because we do not want power under any conditions until we are ready to arm the vehicle. And so for the proton, it will be setting off the primary apogee charge in addition to the separation charge that we talked about previously. And that will be connected via the terminal block. The terminal block will be outside on the bulk plate. And then for the quantum, we will have a redundant apogee charge that it will be setting off. For sustainer avionics, we have a Blue Raven altimeter, which is our primary, and then we have an egg timer proton altimeter, which is our redundant one. And then for tracking, we have an RF beacon, because based off of our apogee, we're going pretty far and we want a more robust RF unit, and so we decided to go with the beacon instead of another featherweight. In terms of how it works, we have the proton, which has a similar screw switch setup as the booster avionics do, and then that will be setting off through the terminal block a secondary apogee charge and a secondary line cutter charge. And then our Blue Raven is our primary, and it will be switched via a magnetic switch that is connected to our power perch, and then that will be setting off our sustainer ignition, and then we will also be setting off our primary line cutter charge and our primary apogee charge. And one note about the sustainer ignition is that we will be having a wire that is going outside from our avionics bay, from the terminal block, onto the outside of the rocket, and that will be covered by a fiberglass layup, and then it will be going, then that wire will be connected to an E-match, which will be going into the motor. And that's it for our presentation. Thank you.